This time, we're going to represent switching networks using our propositions. So again, let's just have a quick recall of how we can do that. So again, remember that we have two main networks that we can represent using propositions. Those are the parallel and the series networks. So the parallel network looks something like this. So if these are your two switches P and Q, and this is analogous to P or Q. On the other hand, our series looks like this. This is your two switches P and Q, and analogous to P and Q. Our conjunction for series, disjunction for parallel. So, we're going to use our knowledge of these analogies to represent our networks. And let's do that on our first network here. So let's just take a closer look into that. There you go. Oops, that's too big. Here you go. Alright, so we have our network here. We have our terminals A and B, and we have switches P, Q, and R. So we can see that switches P and Q are connected like this. And we can make this as an analogy to a series. Not through series, but through a conjunction rather. Hence, we can write this specific part of the network as P and Q. On the other hand, as you can see that this entire series network is connected like this to switch R. That would mean that this entire statement is connected parallel to R, and we write that using propositions as OR. So I'll write R here and P and Q, which represents this network as connected to R parallel. So therefore, this entire statement here, or this entire network rather, can be represented by the proposition P and Q or R. So there we go. That is how we can represent our switching network. There you go. So let's have our second one here. So let's just zoom in. Oops. Let's go to the other side. Here you go. Oops, it doesn't fit. There you go. So now we have this one. So pause the video and try to analyze how we can represent this using propositions. Alright, so you can see here switches P and Q connected parallel. So therefore, we can say that this is P or Q. As you can see now, after this, the parallel network is connected to R via series. So this can be AND R. So therefore, we can write this as actually P or Q and R. So this now represents our second network. So there you go. That's another example of how we can represent our network. Let's go back, and there you go. Alright. Alright, here. So let's now go to the last one here. Let's just zoom in on that one. There you go, and let's just go to that part. There you go, here. Let's just move a little bit. Alright, there you go. So here, as we can see, we have here P and Q, R, and a not P as well. So we have P and Q connected by a parallel, as you can see. So therefore, we can say that this is P or Q. We have another one here. They are connected straight. So we can say that this is R and not P. But these two, as you can see, are further connected by another parallel network. So that means these two propositions can be further connected by a parallel. So let's just pull down that a bit. Alright, so let's just go down a bit. There you go. That's P or Q. Let's remember that. So that would mean that P or Q, we have P or Q and then R and not P connected by a parallel network. That means we have to connect them by an OR as well. So this is the statement that represents this network here up above. So there you go. Alright, so now let's return this to normal view. And let's just pull that up a bit. There you go. So we can see all representations. So as you can see here, we can represent specific networks by propositions using our analogies of parallel and series networks. Now, it's your turn. Pause the video and try to represent these networks using our propositions. Alright, so let's start with the first one. As you can see, we have S connected to this parallel network. So that means we will have S and something. So now as you can see, this is not only just 2, but we actually have 3 switches connected parallel. So that means we have to write this as not R or not Q or P. And all of these 3 switches are the ones actually connected in series with S. Therefore, the statement or the proposition here rather should be S and not R or not Q or P. So this is the proposition that represents this network. How about this second network? So in the second network here, you can see that we have not S and R. They are connected at one street, so that is a series. So we can have this at end. But we have not Q and P connected in parallel. So that must mean that we will have not S, then R here, then we will have P, not Q and P, so I will have N, not Q or P, and R. And the reason for that is, again, take note that not S and R are connected to series with this parallel network, and the parallel network has not Q and P. Finally, we can have this one here. As you can see, we would have not P, Q, not R, and S. This is in parallel, so we'll have not P or Q, also in parallel, not R or S. But the two parallel networks are in series. So that's why we can write this as not P or Q and not R or S. Oops, sorry. Let's fix that. There you go, not R or S. So those are examples of how we write or represent rather networks as propositions.